Hello and welcome to the next installment in the mini-series on calculus at the higher level. And in this tutorial I'll be continuing the discussion of stationary points, and I'll be just essentially going through some examples of how to calculate them for simple functions. The previous tutorial was more of a conceptual introduction to stationary points, just to give you a sense of why they might be important in the application of calculus to science. But for the purposes of the mathematics curriculum, essentially what you need to know how to do is, when given a function f of x, how to calculate the location of stationary points and to determine their nature. Are they maxima, are they minima, or are they the inflection points that I hinted at in the last tutorial? So what's probably a good idea is to, first of all, let's start with a function where we actually can easily figure out the shape of the function and locate its stationary point by hand before we use the power of calculus to solve that problem. So let's, for the first example, look at the parabola. Y equals f of x equals x into 2 minus x. And let's see what this function looks like. We see the function vanishes at x equals 0 and at x equals to 2. So it's going to pass through 0 at x, pass through y equals 0 at x equals 0 and x equals 2. And let's just expand this out. This would be negative x squared plus 2x. And so it's a parabola with a negative value as the coefficient of the x squared. And so we know that it's going to be a hill-shaped parabola. We also know for parabolas from National 5 that the axis of symmetry lies midway between the two roots. So at x equals 1, we will have so-called axis of symmetry. I can try and sketch here at a funny angle. So the function will essentially be symmetric about that axis. And will look something like this. Try and draw a parabola here, so something like this. There we go. It's not a very good sketch of a parabola, but good enough for our purposes. So we have a function which has a single stationary point, a maximum, and that maximum is located at x equals 1. And the actual coordinates of the stationary point, once you know the value of x, are trivial to find because you can just substitute your value of x into the original function. So when x is equal to 1, we see that we have 1 times 1, so that the coordinates of this stationary point are 1, 1. So that was fine. Let's see how we would solve this using the calculus that I talked about, where we want to find the derivative of the function and set that derivative to 0. So let's see what happens if we do that. So the derivative of the function f primed of x is easy enough to determine. We can expand this out into this form, and we differentiate. We get negative 2x plus the derivative of 2x is just 2, and we set f prime to 0 for the stationary point. So that's essentially the recipe, if you like, for finding stationary points, is to set the derivative to 0. So if we do that, we have that negative 2x plus 2 is equal to 0. In other words, that 2 is equal to 2x, so x will obviously equal to 1. And so what we see here is that applying calculus to this problem and differentiating, setting to 0, we get the value of x, giving us the location of the stationary point. We can also determine the nature of the stationary point by just looking to the left and to the right of this value of x. So let me show you how that would work for this simple example. If we look to the left of the stationary point x equals 1, let's say x equals 0, we can now, very important not to put this value into the function but into the derivative. We can see that the derivative of the function evaluated at x equals 0 will be 0 plus 2, so just equal to 2, which is positive, and obviously that we can see that from this curve that the function has a positive gradient of its tangent there at x equals 0. And if we look to the right of that stationary point, and I'm saying say here or e.g. because you can choose which value of x you want to look at. It just needs to be close to the value of x that shows you where the stationary point is, because if you have a function with more than one stationary point, in determining the nature of the stationary point with this method, you mustn't stray too far away from the stationary point, otherwise you may end up on the wrong side of another stationary point and then all hell will let loose. So just choose values of x judiciously which are close to the left and to the right of your value of x at the stationary point. It doesn't matter for this example because we only have one stationary point in the function. So I'm going to look at x equals 2 just because it seems the simplest value to put in. It's an integer. And if I put x equal to 2 in the derivative, I find that the derivative evaluated at x equals 2 is negative 4 plus 2, which is negative 2. We don't need to know the value of the derivative at these neighbouring points, we just need to know the sign. And what we're showing here is that the derivative is positive to the left, it's negative to the right, therefore we see this is a maximum. Sometimes it's helpful just to put this into a sort of mini tabular form. You might just have say x ranging from 0 to 1 to 2, and you'll be looking at the essentially the sign of the derivative for those values of x, and just make a little table. And what we see is that of course at x equals 1 the derivative is 0, that's our stationary point. To the left at x equals 0 we saw the derivative is positive, and to the right the derivative is negative. And what some students find helpful when they've done this table is just to indicate with a sketch of a tangent, and it will very quickly indicate to you what's going on. So a positive slope, a 0 slope, and a negative slope, and you can see that you essentially have a maximum there. So let's look at another example, one where what I'll do, I'll write the function down and I won't sketch it, so we'll actually use the calculus to determine what's going on with the function, and then we'll sketch it just to check at the end, and then you'll get more of a sense of the power of this method. So let's have a look at another example then. And this is an example which may look a bit odd, but it often comes up actually on optimization problems. So it's good to have seen it in this more, I would say, sort of formal setting. So let's look at a function f of x, which is equal to, very simple, x plus 1 over x. And we'll sketch it in a moment, but first let's just go through the motions of differentiating it, setting the derivative to 0, and locating the stationary point. And just for the sake of argument here, I just want to say that x is actually just greater than 0. I don't want to look at negative values of x, or indeed x equal to 0 either. So I'm just looking at positive values of x only. And to differentiate this function, we if we're unfamiliar, if we're not fluent with calculus, we'll want to put this into a form where we're more comfortable. So we'd write f of x equals x plus x to the negative 1. and then having this explicit index here will allow us just to apply the simple rule of differentiating x to a power. So when I differentiate here, the derivative of x is 1, and the derivative of x to the negative 1 is, I bring the power downstairs, and then I have x to a power which is 1 less, so it'll be negative 1, negative, take away 1, which is negative 2. So the derivative of x to the negative 1 is minus x to the negative 2. Let me rewrite this in a form that's actually now more useful for manipulation. So I've sort of gone into the indices form to differentiate. I've differentiated, now I'm going to come back out in order to manipulate algebraically. So this is 1 minus 1 over x squared. If you're unfamiliar with your indices, I recommend just brushing up manipulation of indices from the National 5 level. But a very important thing we use in calculus with indices is that x to a negative power is the same as 1 over x to that power as a positive. Okay. Right, now what we're going to do now is set this equal to 0 to locate the stationary point. So, on setting this equal to 0, let me rearrange this equation. If I multiply through by x squared, I have 1 times x squared is x squared, minus 1 over x squared times x squared is just 1, is equal to 0 times x squared is 0. So I've just rearranged this equation. Therefore, x squared is equal to 1. And because I'm only looking at positive values of x, I have a single solution to this equation, which is that x equals 1. Just by coincidence, there's nothing special about the value of x equals 1 in stationary points. It just so happens that the two examples I've looked at here both have a stationary point at x equals 1. So that's fine. So we know for positive values of x, this function has only one stationary point. It's located at x equals 1. Now let's determine its nature. Now, because I'm confined to positive values of x, I'm going to go to the left and choose the value x equals 1/2. And I'll go to the right and I'll choose the value x equals 2. These seem to be sensible values to choose. So on the left then at x equals 1/2, remember I don't want to put these neighbouring values into the function. That's not what we want to do. Instead, we want to put them into the derivative and see what the sign of the derivative is. So the derivative evaluated at x equals 1/2 will be 1 minus 1 over 1/2 squared. Okay, which is 1 take away 1 over 1/4. Now when you divide by a fraction, you're essentially multiplying by the inverse of that fraction. So this is 1 take away 4 over 1, which of course is just 4. This is negative 3. We don't care about the value, we just need to know the sign. We see it's negative. Let me look on the other side then, to the right. I've chosen x equals 2. So putting that into the derivative, I have 1 minus 1 over 2 squared, which is 1 minus 1/4, which is 3/4, which is positive. So now then, when I make this little table up, I changed x from 1/2 to 1 to 2. I looked at the value of the derivative. Of course, 1 happens to be the value where the derivative is 0. That's our stationary point. And to the left, I find that the derivative is negative. To the right, I find the derivative is positive. And therefore, I can see that I have, in this case, a minimum. Negative gradient, 0 gradient, and positive gradient. I have a minimum for this function. And let's just see if that makes sense. Let's do a quick sketch of the original function f of x. And I'm just going to squeeze it in here because I want to use this precious space here to talk about inflection points briefly. So here we go, just a quick sketch. We're only interested in positive values of x. And what does this function actually look like? Well, it's good practice to just sketch functions here. We have the addition of two terms. We have the first term is just y equals x. So graphical representation of f of x. We have one part of the function is just a straight line, y equals x. And then the second part is 1 over x, which is the simplest really hyperbola, which you may not have come across before, but the function y equals 1 over x looks like this. So this is y equals x, and this is y equals 1 over x. And what we need actually is the sum of these two functions. If I add these together, you can see that 1 over x function goes to infinity near x equals 0, and the y equals x function goes to infinity for large values of x. So the function is going to start very large here at small x and very large for large x, but the smallest value it will have will be somewhere around this crossing point here. So this function will look like this. So there's a sketch. That blue line there is a sketch of the function. If I just extend it a bit, it would go to infinity as x goes to 0. Okay, so there's the function y equals x plus 1 over x. What we have found is that yes, it has a minimum, and that minimum indeed is located at x equals 1, which is interesting because that's also the value where these two different terms actually cross, because they have the same value at x equals 1. So indeed the minimum and the crossing point are all at x equals 1 here, and the value of the coordinates of the stationary point would therefore be 1, 2. Alright, so that's a slightly more complicated example of locating and identifying a stationary point for this function. This is a function that often crops up in optimization problems. Right, so finally in this wee bit of space here, I want to just talk about inflection points. They have less application in science, I would say, although they do occasionally occur, but they are important to know about because they may well crop up on any exams you take on this topic, and plus it's just important that you know of their existence and what they really represent. So we're just going to briefly discuss inflection points. And what I will do is introduce this to you with a very simple function, and you may be quite surprised that this function has an unusual property like this. So let's think of the function y equals f of x equals x cubed. So I want to think of the function y equals f cubed. Now that's a very beautiful function. We haven't really talked about these before. We've talked about straight lines in National 5 and parabolas, but we haven't talked about the function y equals x cubed. And in fact, later in the higher course, when we talk about polynomials, we will get an introduction to what are called cubic functions. And this actually is the very simplest cubic function, but it looks different to the kind of cubic functions that we're going to see when we do polynomials because it's so simple. It has a slightly unusual shape. So let me show you that shape of the function y equals x cubed. Right. So the first thing we notice, of course, is that this function will go through the origin because when x is 0, y is 0. And also when we think about functions like y equals x squared, which is the simplest parabola, this is sort of similar in that it's going to increase quite sharply. It will increase more rapidly than the function x squared, of course. If you think of x squared, when we go from x 1 to 2 to 3, x squared goes 1, 4, 9. But with x cubed, when we go 1, 2, 3 with x, the function will go 1, 8, 27. So you can see it's a very rapidly increasing function. When we go negative, so let me draw the, sorry, let me getting ahead of myself. Let me draw the positive part of this function first. It's a very rapidly increasing function. When we go negative, let's think what it would be, say, for negative 1. We would have that y is negative 1 times negative 1 times negative 1. Well, negative 1 times negative 1 is just 1. Multiplying again by negative 1 gives negative 1. And indeed, we get all the same values that I mentioned, 1, 8, 27. However, they're all negative, so the function will look just the same as this, but negative. So that's what this function looks like. I haven't actually drawn it brilliantly well, sadly, but it sort of looks like this. What you can see here is that around the origin is where the interesting stuff is happening, and let's do a stationary point analysis and see what we find. Let's set the derivative of the function to 0. If I calculate the derivative, that's very straightforward. I just get 3x squared. I'll set that to 0 for stationary points. What I see is that I only have one solution to this equation, which is x equals 0. And that's consistent with our sketch here. We don't see anything happening for non-zero values of x in terms of stationary points. This is just going to go to infinity. This is going to go to negative infinity. All the action is around the origin. So we have a stationary point at x equals 0. If we look to the left, let me take x equals negative 1. Now I'm not going to put this into the function, of course. I'm going to put it into the derivative. So to the left, the derivative evaluated at negative 1 will be 3 times negative 1 squared, which is 3 times 1, which is 3, and that's positive. And when I look to the right, I'll just choose x equals 1. I have that f primed of 1 is just 3 times 1 squared, which is just 3, which is also positive. So you can see then for this example that the derivative is positive both for x left of the stationary point and x right. And of course that's clear from the graph here. If I just say this is x equals negative 1 and this is x equals 1, and I look at the tangent here, you can see that both tangents are positive. So this is a case then where if we were to draw one of these little tables, we have x going from negative 1, 0 to 1, and we have f primed. In this case, going from positive value at negative 1 through 0 at the location of the stationary point, and then positive again. Okay, so that's a signature of what you might call a positive inflection point, one where the derivative goes from positive before the stationary point to positive afterwards. And just for completeness, let me draw a tangent to the curve at the origin. Can't really see it, but it would be essentially a horizontal line at the origin. I didn't draw this brilliantly well, but that's roughly what the x cubed function looks like, and it does have a 0 derivative at the origin, as we've actually shown here. So that's an example of an inflection point. The so-called negative inflection point would be for a function such as negative x cubed. So if I had a function negative x cubed, for example, which would look like this blue dashed line, you can see we'd have exactly the same analysis, but we'd have a derivative that goes from negative through 0 to negative. So if you are given a function which you're unable to graphically analyze, so you really don't have a sense of what's going on, and you set f prime to 0, when you calculate f prime, you set it to 0, you locate the stationary points, When you do this analysis of looking to the left and the right of the stationary point, if you do find that the derivative goes from positive through 0 to positive, or negative through 0 to negative, then indeed you have identified an inflection point, and around the location of the stationary point it will look like this curve. This sort of x cubed, if you like, is sort of a poster child for inflection points. So I hope that's been helpful. We've just gone through some simple examples of evaluating location and nature of stationary points. You might be asking, do we really have to create this table every time to find the nature of the stationary point? Well, at this level of mathematics and the Scottish curriculum, this is the method that they seem to recommend. If you were to be doing advanced higher mathematics, which is really the next stage in the Scottish curriculum, it would be equivalent to sort of A-level in England, then essentially you would use a slightly more sophisticated technique, which is also, to be honest, faster, and that would be calculating something called the second derivative. And the second derivative tells you the rate of change of the derivative itself, and the sign of the second derivative would immediately tell you whether you have a maximum, a minimum, or an inflection point. And for these inflection points we would find that the second derivative actually vanishes, and that would be the signature of an inflection point. But let's leave it here for now, because at the higher level this is a perfectly adequate and expected response in determining the nature of stationary points. So what we'll do in the next tutorial is apply this to so-called optimization problems. What I'll do is make up a very simple example of an optimization problem, and then we'll go through an actual past paper optimization problem to see sort of how this works in more detail, and you'll see then a nice sort of simple application of stationary points to, somewhat in quotation marks, real-world problems. So I'll leave it there. Thank you so much for your attention and for supporting these videos, and I will see you next time.